Great. Okay, guys. Lab report's due today in lab and Friday in lab. The next lab is the diol oxidation. In the lab manual, it calls for a lab report. Instead of a lab report, we're going to have an answer sheet. This is the answer sheet going around. It's yellow. I reckon we'll do 2 stacks. Same thing. Answer sheet for this week's lab. Any questions about this week's lab? Diol oxidation. We'll start oxidation of alcohols today. That handout was given last week. It's a purple sheet, lavender, and a white. Let's finish up. Let's look at the quiz real quick. Number 1, good old classical Williamson ether synthesis. Sodium makes the alkoxide. The alkoxide does an SN2 on 1 bromopropane to give that ether. How do we do? Pretty straightforward. HI with this ether, only thing we can do is protonate the ether. Then we have I nucleophile. Do we have a tertiary site available? No. So we're doing SN2, less substituted site, kick off the oxygen. These are the 2 products. We have inversion here, there's R there, and so this is now S. How we do? Questions? Alkyl halide with magnesium makes Grignard. It's essentially the carbanion. We put in the epoxide. Carbanion does SN2. We tactily substitute the site, kick off the oxygen. Aqueous workup puts H on the oxygen. How we do? Questions? Making the epoxide, MCPBA, or peroxy acid or something, right? Mechanism of H2SO4 catalyst. What's the first thing you want to do? Protonate something. Protonate the epoxide. From there we have a tertiary site available. We can ionize and make carbocation. What size ring do we want to make? 5. Oxygen is attacking something. If oxygen attacked this, either one of these carbons, it'd be 7 or 8. Make carbocation because it's a tertiary site. We can do resonance. Resonance arrow. Now we have this cation here that the oxygen can then attack, make a 5-membered ring. Remove the proton, we get product. How we do? Question?
So with the oxide, it just opens up when you protonate it? And it's all
Right, there's 2 types of reactions for epoxide, SN1 or SN2. SN1 would be opening up, make carbocation. When are you going to do that? Whenever you have a tertiary site available? Yeah. It's a nice tertiary site to do carbocation, like SN1. It's basically an internal SN1, except we have some resonance in there. How'd we do? Question?
Did the epoxy problem up above have a tertiary site? No, the one up, I think it was number 3.
This is strong nucleophiles. Strong nucleophiles always do what?
Yeah.
SN2. Right? Look back on the outline. Strong nucleophiles always SN2. You only have to choose when you've got a weak nucleophile and a protonated epoxide. Strong nucleophile always SN2. Y'all want to repeat that with me? Strong nucleophile with epoxide always SN2. Look for things that make it easy. Good question. Question, Matt.
The one with the deuterium. Why can't it attack from the left side?
Because are we doing SN1 or SN2? SN2. Which site do you want to attack with SN2? Which is least substituted? Over here with 2 carbon substituents or over there with 1? A deuterium is not a carbon substituent. A deuterium is just a funny looking H. It allows me to do some stereochemistry there though without getting more substitution. You see deuterium used in organic 1? Okay. All right, these will be posted up. This will be posted on the 3rd floor in the bookcase as you head down to the lab. If you have any questions, let me know. One of the main purposes of the quizzes is to help you learn, see what you need to be looking at so you don't make the same mistakes on the test. Okay, let's finish up the epoxide handout. Where are we at? Where is it? There it is. We did that one, yeah. Did we do that one in class? How about amines? I don't know that we did amines. We do this one in class. Got this epoxide, we got this nitrogen. sp3 nitrogens are good nucleophiles. Epoxides can be opened up by SN1 or SN2. What mechanism do we want to do here? SN2. Amines are good nucleophiles, strong nucleophiles. Which side do you want, top or bottom carbon? Bottom. Take off the oxygen. If we've got a strong nucleophile, the oxygen will leave without being protonated. By the way, we have no proton. You can't protonate it. There's no acid here. What does this give? Well, we have the methyl. We have the oxygen to the left. The nitrogen is now bonded down here. But since the leaving group is forward, on that carbon, the nitrogen comes in from the back. So it would be as if it came in from the back, and the nitrogen has 3 H's. That is an intermediate. Nitrogen makes bond to carbon, oxygen has left. At this point, this needs a proton. That needs to get rid of one. We can do an internal proton transfer, an internal acid-base reaction. We're just going to call this H plus transfer. I'm not even going to show an arrow movement because it's probably, as I showed last time, one molecule of 1 O minus of one molecule taking the H from another molecule. H plus transfer. We'll do it about 100 gazillion times this semester. And we get the final product, which looks like, what is this now? There's only 1 H there. No, there's 2 H's. And a lone pair. There's your product. Nitrogen has added to the epoxide, opened it up, followed by a proton transfer. Uh-huh.
With the proton transfer, is that similar to hydroboration?
No, hydroboration is a hydride transfer. I'm not transferring hydride, I'm transferring H plus. You should look back at the mechanism, make sure you understand what's going on there. What do we have? That's the nucleophile, yeah. Wasn't the amine the nucleophile? But the amine has to lose an H to go neutral once it's making another bond. Nucleophile, carbon, carbon, OH. Didn't we say that's what epoxides give? Standard, unless you do some fancy rearrangement or something. Well, below, it's the same thing, except we're just doing 2 steps. What does MCPBA do? It makes the epoxide, right? And then this is nitrogen, yeah? Just like that, except it's got a methyl. Which carbon do you want to attack, left or right? Here, open it up. We have ring. Oxygen here. I'm not going to do the proton transfer, but isn't that the product? Nitrogen adds to carbon. Oxygen gets kicked off. It eventually gets protonated. This loses an H. It's not going to lose a methyl. You can work through here. It's just like the one above, except it has a methyl on the nitrogen. And we just made the epoxide first, right? Other strong nucleophiles. Why don't you show somebody have product for this one? What's the nucleophile here? MeO minus, right? Right there. That's a minus, K plus. Do we have an acid catalyst present? No. So you're not doing an acid protonated epoxide where you have a choice between SN1 and SN2. All you have is a strong nucleophile. Weak nucleophile doesn't do anything unless it's protonated. There's no proton. You can't protonate. You can only use the strong nucleophile. Because we're using strong nucleophile, SN1 or SN2? SN2. Left carbon or right carbon? Left. Kick off the oxygen. What do we get? Here's the epoxide, 2 carbons. The oxygen leaving group is straight up. See how it's straight up? That means the new group is going to be straight down. And that's what? O-methyl. The methyl's still there. It actually gets pushed up. When this opens up, the oxygen is straight up. And we have that and this. Show that minus. Does that look right if it opens it up? You get an inversion here, but no change there. Any questions about that one? I sense half of you are struggling with the stereochemistry. Everybody's got the stereochemistry? No? Question?
When you just drew it like that, you still have it coming out. So how is that inverted?
Well, it's just RS. 1. Carbon and everything else is 2. Methyl's 3. H is in the back. There's an H there that's going back. That's R. What is this? 1. Carbon with oxygen is 2. Methyl is 3. 1, 2, 3. H is in the back. This is S. It's inverted. The nucleophile came in opposite the leaving group. The leaving group is straight up, so the new thing is straight down.
I see it. Just in Idell's class, if it was inverted, we just drew it the other way.
Here's this carbon. That carbon there is right here. It's got oxygen straight up. It's got a methyl forward.
Right. No, I understand it now.
Here's the oxygen straight up. Okay, there's the oxygen straight up. Methyl's forward, coming towards y'all. How does a nucleophile come in? Right here, it kicks the oxygen off. Okay, when this comes in, kicks the oxygen off, these two just move up like this. But it's still forward.
Right.
as opposed to doing it like this. Now, if you want to turn this around like this, now the methyl's going back. I mean, if you want to show it like this, methyl's going back, and the nucleophile comes in from my chest, kicks the oxygen off, what does it do? It moves these forward. Now that's back to forward. Here, we're going down to up. But the elbow is still forward in both cases. So you've got to fundamentally understand what inversion is. We got to put a proton on. What can be a source for the proton? The methanol can be a source for the proton. Or you can throw in water. But basically, you throw in, with methanol around, this will take an H from methanol, and we can go neutral. So when you have a protic solvent, the protic solvent can supply the proton to go neutral. We looked at a brief for the multi-step synthesis. If you look on the back side, there's others to work. You need to be starting to work some of those, be looking at them. After we go over oxidation, we'll come back and look at these near the end of test 1 material. Please be looking at some of these though. Real quickly, just to kind of a miscellaneous topic, but very important. Epoxides can be polymerized. If you've ever heard of an epoxy glue, anybody ever worked with epoxy glues? What do you have to add to them to make them turn into a glue or something? Don't you have to add something to them? Like a curing agent or something? Anybody ever done this? Basically, the glue is a monomer, and you add something to it, you make it become a polymer. Ethylene oxide is the simplest epoxide. Ethylene is just a 2-carbon alkene. Ethene, but it became known as ethylene. If you turn this into the oxide or oxygen, it's called ethylene oxide. It used to be used to sterilize surgical equipment because it's very reactive, it'll kill microbes. Treat this with hydroxide, you can envision the monomer. Because this attack, either carbon, kick that off. What do you get? Nucleophile attack, kick off the leaving group. And then this can just pick up a proton from the water, acid-base proton exchange, and we can get that. Okay? That would be a diol. You can also get polymers out of this. In fact, polymers are very prone to happen. So let me show this taking a proton from water. And we would make that, we'd actually reform hydroxide. So that's a simple mechanism, yeah, hopefully. How can we get a polymer? And a polymer has, by the way, repeating units. And the repeating units are usually shown in parentheses with an N. Some type of integer, some big number like 100 gazillion. Huge molecule. Repeating unit. How could we get that? Well, some of this O- taking a proton, what else could it do? It could attack another epoxide. And if it did that, these electrons add here, open that up. What does that give? That gives the nucleophile, which was this, added to the carbon, there's the 2 carbons, opens it up, and we just made that bond. We could get this. Now this could pick up a proton and become a dimer, But what else could it do? It could attack another epoxide. And this could attack here. Open that up. What do you get? Let's see. We get OH, oxygen, do. We just made that bond, and that becomes O minus. What can this do? This could attack another epoxide. How many times do you want to do it? 100 gazillion? It'll do it like that, 100 gazillion times. Keep on going, and you'll end up with what? What kind of repeating unit can we see in this long molecule? I start right here, CH2, CH2O. CH2, CH2O. CH2, CH2O. Keep on going as many times as you can handle it. So we can show it sort of like this. OH on the end, CH2, CH2O. 100 gazillion times. Eventually it'll become CH2, CH2OH. Eventually this will pick up a proton. Now the polymer length will vary tremendously. And when people make polymers, one of the first things they have to do is figure out what are the different lengths in their mixture. And they can control the length. Depending on the length, they can get different properties of their polymers. Polymer chemistry is a huge field. Does it make sense how this can sort of polymerize? Now if you have some glue like this, all you got to do is just drop in a little bit of base to start it off. Polymerizations, there's three types of polymerizations. Cationic, anionic, and radical. Based on what initiates the polymerization. What initiated this polymerization? Anion, a cation, or a radical? Anion. This is an anionic polymerization. Not written up there, but okay. If you have a polymerization initiated by acid catalyst H+, that would be a cationic polymerization. This is an anion. Any questions about this? When you're dealing with epoxides, they're very prone to polymerize. Even all the reactions we've done before, all of them are susceptible to polymerization. If you ever work with epoxides, you always got to watch out for that. Your yield can often be low because instead of getting your desired product, it'll polymerize. Questions about how it can polymerize? Self-react over and over with itself?
How do you get it to solve?
That's that polymer. You need to ask the polymer chemists. They spent lots of research going into controlling their polymerization. And again, short polymers may have some properties. Longer polymers may be more brittle, harder to mold. Huge field of controlling the polymerization. You buy stuff like that at Walmart, Lowe's. Okay, there's an epoxide puzzle. If you remember in Organic 1, I gave you one about alkenes. Here's an analogous one about epoxide. A good review. Probably a little quiz, a little puzzle there. Was the sodium atom certain it had lost an electron? You fill in down the bottom and you answer that riddle. There's a number of miscellaneous things in here. I don't want to cover them now, we don't really have time. Please look ahead. Synthesis of Prozac includes an epoxide. You're familiar with any of the antifungal drugs? Lamisil type of stuff? Or athlete's foot and all that? You see those commercials? How do those drugs act? They inhibit the enzyme known as squalene epoxidase. You can read about that. How's cholesterol made in your body? Your body makes an epoxide and then goes from there. I include things like this to show relevancy. If you're interested, do. If you're not interested in this stuff, well, that's up to you. Sometimes I'll take time and go over it. Sometimes I'll just let you ask questions about it. We don't have a lot of time to go over all the applications, but there's plenty of them. The one with the cal, there's a synthesis down there. We do need to be looking at synthesis, so I would highly recommend this one. When you see this type of here, you're going backwards. This is the retrosynthesis arrow. Y'all have hamburger meat? Feed this to cows to make them bigger. Make the cows 10% bigger. So the farmers can make 10% more money. I think on the very back there's a sheet of the oxide questions that got left out of the workbook. That's them here. On the back side is the answer key. I recommend you not look at the answer key until you struggle with the problem so well. And then hopefully on the very front you can now look at these mechanisms for the leukotriene synthesis. Okay, let's look at the alcohol oxidation. Lavender sheets to warm up. Major reaction of alcohols is their oxidation. Oxidation to a carbonyl compound. For example, if you see estradiol, what does the diol mean to you? Got two OH groups here. It's converted to esterone. What does the ON ending mean? It's actually going to be a ketone. We'll see ketone nomenclature later. But what we'll see here is the OH has been oxidized to the carbonyl compound, the ketone. In terms of formula, what's the difference? What does an oxidation do other than make a ketone? Well, importantly, and there's also an H there. The two H's are removed. And now you have the double bond. There's no H here, and there's no longer an H there. So it's oxidation. Oxidation is usually written with an O sometimes, but sometimes maybe an OX. Just generic for, hey, oxidation is taking place here. Also, sometimes it may be written like this, because we are losing two H's. Not as H2, but just from the formula. How do you judge an oxidation? In Gen Chem, you judge it by oxidation state of the metal. For example, if iron went from +2 to +3, we said it was oxidized because it lost an electron. Oil rig, oxidation is lost, reduction is gained. In organic, you don't see the electrons as easily. In organic, there's two ways to judge redox. If you lose H's, that's an oxidation. Now you can go backwards. We'll do this during tests 3 and 4. Right now we're going forward. If you go backwards, you're doing a reduction. That's usually drawn with an H. It's like, hey, we're reducing. To go backwards, don't you have to add two H's? It would be a reduction. Loss of H's is oxidation. The second way to judge redox in organic is number of bonds of the carbon to a more electronegative atom. Here the carbon has one bond to a more electronegative atom. How many bonds to a more electronegative atom does the carbon now have? 2. A double bond to oxygen. If you increase bonds to a more electronegative atom, that's also known or illustrative of an oxidation. 2 ways to judge it. Okay. Now, of course, when you get to biochem, you'll learn all the about all the steroid pathways. The one that on the front sheet circled there. So, oxidation of alcohols. If you have a primary alcohol and you do an oxidation, you'll first get to the aldehyde. I've just turned it, but if we were, there are 2 H's here, right? Why did it go dark? It wasn't that dark there. Hope you can see it. If we remove the 2 H's and put in a double bond, what do we get? Double bond to O, but there's 1 H left there, right? We only removed, well, that is that. I've just got it turned, right? Now we'll learn that aldehydes are actually susceptible to further oxidation. You do have to have water present. And aldehydes can be oxidized to carboxylic acids. How do we know it's an oxidation? We're not removing H's. But what are we doing? This carbon has 2 bonds to a more electronegative atom. Now that carbon has 3. You see, it's an oxidation. Yes, we're also adding oxygen, which is actually another way too. We're adding electronegative. I don't know why it got darker than it was. Oh, it's lighter right there. Okay, secondary alcohols, if you oxidize them, remove the 2 H's, you get the ketone. Because 2 H is gone, that becomes double bond. Ketones are not susceptible to further oxidation, at least not in this class. They actually are, but not in this class. Never in this class. Lots of stuff we say is not possible in this class actually can't happen. Tertiary alcohols cannot be oxidized. There's no H here, right? Since there's no H there, you can't make a double bond. You need to have 5 bonds to carbon, you'd have a Nobel Prize. You can't oxidize tertiary alcohols in this class. What are common oxidizing agents? Usually they're recognized by having lots of oxygens in them. I will talk about the big 3. Dichromate. Cr2O7 2 minus, and that's 2 plus. You can either have sodium or potassium dichromate. That's one of the big 3, dichromate. Chromium trioxide or potassium permanganate. They all have oxygen, they're all heavy metal, they're all little toxic or environmentally unfriendly. There's other oxidants out there, but these are going to be the big 3 that you kind of see in your textbook and in the introductory organic discussion. What are we using in lab today? We're not using one of the big 3, we're using calcium hypochlorite. Sodium hypochlorite is bleach. Look on your bleach bottle at home. You could use sodium also, but sodium hypochlorite is not that stable and it can't be stored. Calcium hypochlorite is a little more stable. That's what we're using in lab. The mechanism is just an E2 elimination. But instead of forming a C double bond C, we're forming a C double bond O. Let's look over on the white sheet for a little more detail. Here are the big 3. Usually this reaction is done under acidic conditions. Sulfuric acid, acetic acid, or whatnot. Now, I'm not going to talk about KMnO4, but with these 2, the chromium, with either one, Either one forms chromic acid upon being treated with proton acid. So both of these are actually sources of chromic acid. And that's a structure for chromic acid. If that's a sulfur, it looks like sulfuric acid, but it's chromium. Chromium has an oxidation state of 6, and it's orange. If you bring in an oxidizable alcohol, either primary or secondary, the chromic acid will oxidize the alcohol to the carbonyl compound. So it gets oxidized. The chromium reagent must get reduced. And indeed, it goes from chromium 6, it actually goes to chromium 4 first, but then from chromium 4, it quickly goes down to chromium 3. That's a reduction, right? Chromium 6 to chromium 3, it's gaining 3 electrons, that's a reduction. Chromium gets reduced, the alcohol gets oxidized. Chromium 3 is actually blue. So in this reaction, your orange reagent turns to blue. Because of that, it's actually a visual test called the Jones oxidation test. It can be used. Primary and secondary alcohols turn orange chromic acid to blue. They effectively reduce the chromium. Tertiary alcohols don't do anything. Thus, if you add the orange and it doesn't do anything, it seems like you have a tertiary alcohol. Does that make sense? Actually, if you do a breathalyzer test by the local police side of the road, they want you to blow into that little device and they want to see how much orange you turn to blue. If you blow and all the orange gets turned to blue, they'll give you a free ride downtown. They're doing a spectrophotometric analysis, just like this. All that alcohol, ethanol, will oxidize. If you were drinking tertiary alcohol, you wouldn't have any problem. At least not a problem with breath analysis. You'd have other problems. Please read ahead. The mechanism. I didn't show a mechanism here. We're out of time. We'll show a very brief mechanism for how this actually takes place. But for now, predict the products. Please be doing some reading about this. And you got the pre-lab today for lab. See some of you this afternoon, guys.
Like this.